this video we'll be looking at Boolean theorems, and essentially Boolean theorems are a whole lot of rules within Boolean algebra which explain how the system's working and allow us to simplify often expressions and modify expressions. We've got a few different types of theorems. We've got single variable theorems and we've got multivariable theorems where we've got more than one variable, typically two variables. And for each of these theorems that we'll look at in a moment, and there's quite a few of them, assume that x and y are Boolean algebra variables that can either be 1 or a 0. Most of these are fairly self-explanatory and follow the sort of conventions that we'd expect anyway. So let's go through them. So first few relate to the AND operation. So x and 0 equals 0. So we AND anything with 0, it equals 0. X and 1 equals x. If you have a think about it, that's going to hold true. X and x equals x. So x is either 0 or 1, so 0 and 0 is equal to 0. 1 and 1 is equal to 1. And x and not x is equal to 0. Because if x equals 1, not x equals 0, and vice versa, so they're never going to both be high. The next ones, 5 through to 8, correspond to the OR. And think about these, they're fairly obvious as well. X or 0 equals x, so it's only going to be high if the input's high. X or 1 equals 1, because anything we OR with 1 is going to be 1. X or x equals x, so that's essentially the same as what we had previously with the AND. And x or not x equals 1 as well, because one of them is going to be high. Now for any of these, we could very easily write a little truth table. For example, if we're going to prove the first one, we can write out all the inputs and we can write out the corresponding output. We could show for any value of x and 0, our output's going to be 0. Now we also have a number of multivariable theorems, and these multivariable theorems don't just have the one variable anymore, they've got more than one. So the first couple are commutative ones. So it's essentially saying x or y is exactly the same thing as y or x, and likewise for AND. X and y is exactly the same thing as y and x. There's no difference relayed in which variable we put first. We then have a couple of associative ones that essentially say, well, if we put some brackets there, it's not actually going to change anything because they're all at the same level of precedence. We then have a couple of distributive ones which show us how we use brackets if we're multiplying things out in terms of ANDing things together. And then there's a few other ones as well, and some of these other ones become quite obvious. So for example, x plus xy, well, it's going to equal x because it doesn't really matter what y equals. That's kind of built off one of the previous theorems. Likewise, x plus not x, y, is really just x plus y. And finally, not x plus xy is equal to not x plus y. So we can go through any of these and prove them in a truth table to ourselves, and go through all the left and right hand sides, and we'll find that each of those left and right hand sides are equal to the same thing. So one of the things we use these theorems for is simplifying Boolean algebra expressions. So here we go. We might have an expression like this one. Y is equal to A not B C plus A not B not C. And so we can take these theorems and apply these theorems and simplify the expression. So what we can do is we can take out a common factor here of A and not B, and we have C and C or not C in our brackets there. And one thing we know is C or not C is equal to 1. That was back from theorem number 8 that we had here. X or not x equals 1. And so what we have here is, so y is equal to A and not B and 1. Well, the 1's a bit redundant anymore, isn't it? It's the input that we don't need to have. So we've simplified this expression with 3 different inputs and 2 different terms in there into one little logic gate there, which is just an AND gate. So that can be quite powerful as well. Some other Boolean algebra expressions that are useful for us to have are De Morgan's theorems. And these theorems are very, very powerful, particularly when we're trying to convert our circuits to use just NOR gates, which is what our first theorem there's for, or to use just NAND gates, which is what our second theorem there's for. And we can expand these theorems if we've got more variables than these as well. So here we've got an expression that we're going to simplify using De Morgan's theorem. We use De Morgan's theorem. We use the first of De Morgan's theorems to simplify it, and then the second one we simplify it down further, which gives us not A and not C, or B and not C. So we can step through each of those theorems and implement them. Now we mention those theorems because one thing that we use quite commonly is, rather than having a whole bunch of different gates in our circuit, we can actually use NAND gates, and we can use NAND gates, or NOR gates for that matter, to actually represent any of these other type of logic gates. We just have to be a bit clever about how we use them. This means that in our circuit, we only need to use NAND gates. We can replace everything else with NAND gates. So we need to work out how to encode our OR and our AND and our NOT operations using just NAND gates, and it's not very difficult. Firstly, let's do NOT. If we tie our inputs of our NAND gate together, so here we have our 2-input NAND gate, we tie them both to A, essentially that is an inverter. So if we put an inverter on the output of a NAND gate, that essentially removes the N part, the NOT part, and so it gives us a straight AND gate. And likewise, if we want to create an OR gate, essentially what we need to do is we have 2 inverters going into a NAND gate, and that gives us an OR gate. So we can represent any of these type of gates, our inverters, our AND gates, and our OR gates, just using this NAND gate, which makes it very, very powerful. So if we want to convert this circuit here to just using NAND gates, we could do it as follows. We just replace those diagrams in there and convert these over. But you'll notice we actually have a little bit of redundancy here. The output of our NANDs, we're actually inverting twice. And if we invert something twice, we change the value and then change the value again, we can just remove those elements and simplify it right down. And so this will give us exactly the same logical behavior as before. We can also do this very easily using some Boolean algebra and using De Morgan's theorem. So we take the second of De Morgan's theorem, it puts things nicely in a NAND gate form. So for our circuit here, we've got Z equals A and B, or C and D. Now if we invert both of those to get it into a form similar to De Morgan's form, we see there we've got Z bar bar A and B, or bar bar C and D. That's very similar to the right-hand expression of De Morgan's theorem. We then take that right-hand expression and pull it over to the left-hand expression, and we've got our circuit there in NAND form.